Okay. Right. So, yeah, welcome everyone. I hope you all had a good weekend. So today we're going to finish the lessons about Rust. I think we needed to cover a certain amount of Rust, obviously, to give you enough to start writing some code. So today we're going to finish that off and then move back to looking at Solana specifically. But what I'm going to cover today is one of the areas that people often find the most difficult to understand and to get to grips with in Rust. I certainly did. And I think the reason for this is because this is something that is quite unique to Rust. So Rust has gone in a certain direction to solve a problem. And it's done something quite unique, but it does take a little bit of getting used to. But I think if I can hopefully explain to you what they're trying to achieve and the way that they've tried to achieve it, then that will make things easy. It will make it easier for you to understand what has been done and to understand how you should be writing your code. And if you're getting errors, it should be easier for you to understand where they're coming from and how to correct them. So if we go back to the beginnings, really, the problem we have with computer languages is that we end up, we need to create and look after areas of memory. And particularly, we're looking at things what's called on the heap. So this is a large area of memory where we can just create large objects. And when we do this, we need to be able to do this safely. We need to be able to make sure that we're not overwriting a piece of memory that is being used for something else. And we also need to make sure that we're not leaving items on the heap that are no longer being used. And the idea of getting some internal safe memory state and is often called things like dangling pointers. So you'll have a pointer that is meant to be pointing to some particular area of memory. But maybe that area of memory isn't being used for what you expect anymore. So that could then be a problem, because if you're using and you're pointed to write that area of memory and you're writing to that area of memory, then you could be overwriting something that you shouldn't be overwriting. And then, yeah, on the other side, if you've left something on the heap and you're lost track of it, then you'll end up running out of memory because you've got all of these extra objects that haven't been safely removed. And some languages vary in how they deal with these issues. So, for example, languages such as C, C++, they expect you to keep track of what is on the heap and to manage that memory yourself and to work and to do all of the hard work yourself, which is problematic because it's easy to get it wrong. And it's just a hard thing to have to keep track of yourself. Then other languages try to help you by having a thing called a garbage collector, which is meant to go in there automatically and look for items that are no longer being used, and then to safely remove those, which is okay, but then we have less control over that. And this can lead to some problems. For example, with performance, it can make things a little bit unpredictable. You don't really know when this garbage collector is going to kick in and start to get rid of these extra objects. And that can be a problem as well. And so Rust has taken quite a different approach to this, in that it does allow you to have control over what is happening, but then it puts some strict rules around that to make sure that you don't do anything wrong and that you don't get into an unsafe situation. And some of the terminology we use when we're looking at this is the idea of ownership. And this is quite straightforward. When you have some variable that is being equated to some object, some value, then you're saying that variable is the owner of that value. It owns that value. And of course, it could be more complex than this simple example here, where we have this variable myVec, which is owning a vector. Because you could, that vector could be made up of further objects and further variables. So you could end up, rather than just having two items here, you could have this ownership being a large sort of tree structure and go many layers deep. But whatever the case is, we still want to be able to handle this efficiently and safely. And so what we want, the things we want to avoid is that if the vector itself, the value, is no longer in scope, so it is that area of memory is not being used for that vector and is being used potentially for something else, then myVec will end up pointing to maybe nothing, or potentially something else in memory that it shouldn't be pointing to. It will no longer be what we're expecting to be there. Or the other way, as I said about the things are being cleaned up, if the variable goes out of scope, so we no longer have a handle or any owner of this object, but that vector is still there on the heap and would just never get found again. So those are the things we want to avoid. So there's kind of there's two sides to it. So there are some rules about ownership in Rust. So there's this basic one, I just really explained, in that every value in Rust has an owner. There's some variable that is its owner, and it can only have one owner at a time. Once the owner goes out of scope, then the value will be dropped. So this is the way that Rust knows that that value can be got rid of, because the owner variable has gone out of scope. So if we have an example of that in this piece of code, we have the owner variable here is s. This is owning a string. So we've created a string from a string literal. So that string now is the value, and that is being owned by s. And we can do various things with that. But when we get to the next bracket, then the s goes out of scope. So s is no longer valid, and then the value, the string, is dropped as well. So that illustrates things getting out of scope. As an aside, I should say the reason we have this, we're creating a string from a string literal, is that, like many other languages, string literals are handled in a special way in Rust, so they're not, a string literal itself is not created as an object on the heap. So that's why we're creating a string from that. Okay. So this does not apply to all data types. So some data types called copy types, they don't exist on the heap when you create them. They just exist on the stack, and so these we don't have to worry about. With the runtime will look after those. Okay, we don't have to worry about their lifetimes at all. We can just use them in the same way that we would in any other languages. And these are the simple data types, such as the sort of integer types, bools, floating types, floating point types, etc. But then tuples can be handled on the stack, but only if they contain those copy types already. So you can't have, for example, a string in a tuple and expect that to be handled on the stack. Okay. So, but for more complex data types, we need to apply the ownership rules and understand the ownership and the lifetime of the variable and the value that it owns. Now, the thing that Rust does that is quite unique, and the way it enforces this idea of something being owned and only having one owner, is the idea of what is called a move. And the idea behind this, and this is something that you don't see in other languages, is that as you assign values to variables and assign variables to each other, the ownership will move between those. And if you make an assignment of a variable, then the source, the original owner of that value will give up ownership. The new variable will get ownership of that. The original owner, the source, at that point becomes uninitialized. So if you look at this piece of code here, we start off with A owning this vector. So this vector has been created and it is assigned to A. So A is now the owner of that value. Then on the next line, we have another variable that we assign A to that variable. So what's happening there is that we have a movement and the ownership changes here. So this vector used to be owned by A, but now it is going to be owned by B. And so this is the thing that is quite different in Rust as compared to other languages. You don't sort of have this idea going on in other languages. But then which is fine in those first two lines, because now the vector has a new owner, which is B. But the problem that we do get is if we then try to assign A to another variable, because A now is uninitialized, this is not the owner of a value. So this then is a problematic line, because the original source A here is now uninitialized, and so you would get an error if you tried to do this. So what the Rust compiler is doing is keeping track of the ownership of all of our values, and in doing this, it can ensure that each value only has one owner, and that this owner we're keeping track of this owner. It's not being lost in any way, that all of our values do have an owner, that we're not going to end up with a value without an owner, or an owner that has lost its value. So it's a way of making sure that we're applying the ownership rules correctly. Now, I've given a simple example here where we're assigning variables to each other, but this applies to all situations. So, for example, if you're passing a variable into a function as an argument, so you're passing the argument in to a parameter within a function, then this is also a move, and so the ownership will transfer there as well. So the original the original variable will lose ownership of that value, and the parameter within the function will then gain ownership of that value. Now, so this gets well, not too complex, I guess, but it means that it's happening in a lot of places. So you do have to keep track of this and be aware of this. Obviously, the compiler is going to be there to tell you if you've got this wrong. And we need to be careful with the flow of control in code, because we could get a situation where a variable becomes uninitialized. And again, this may seem a little bit unusual when you're coming to Rust new from other languages, but if you think it through, it does make sense. So we start off here with our vector, and that is owned by A. And then we're going into some kind of loop here for whatever condition that is, and we're going to try to pass this vector into another function G. Now that is okay the first time round, but then what will happen is that A no longer is the owner of this vector. So the first time we do this, the parameter within G now owns the vector. So A is now uninitialized. So if we then come to the next iteration and try to do this again, then A is initialized. It no longer has ownership. So this will also be a problematic line here. This will also be an error. Now, there are ways to help us with this and deal with collections. So they do have functions within them to help you with this and to try to make this simpler. So you can write loops in such a way that this is not problematic. Just got one example here of being able to add into a vector. So this is going through, iterating through the vector, and then it goes through and then pushes. Sorry, yes, this goes through. It pushes an item onto the end of the end of the vector. Okay, so that's the kind of the basic rules of ownership. But one of the ways that Rust makes this much more flexible for us, makes this much easier for us to deal with this, is with the idea of references. These are written, as you can see there, so with the ampersand and then the variable name. It's pronounced ref a here, for example, just because this is a reference. If A has type T, then ref A has type ref T. So references are a way of dealing with some value, but without getting ownership, without doing a move of the ownership for that value, because a lot of the time we don't want to do that. Maybe we just want to read a value and pass that into a function, but we're not trying to change the ownership. We want the ownership to remain as it was, and the references have no effect on the reference lifetime. So we don't have to worry if the reference goes out of scope. This does not mean that the referent will then get dropped. So we can use these much more freely. We can be a lot more flexible about how we use these. And this process of assigning a reference to a value is called borrowing the value. But there are still rules about this, because we still have to be careful and make sure that we don't have items that are pointing to things that no longer exist, for example. And there are two types of reference. The easiest to handle is a shared reference, which is really just reading some value that we have borrowed. So we can borrow, and that gives us a reference, and we can read that value and use that, but we can't change it. We can't mutate that, and we can do this as many times as we like, because we're not having any effect on the value that we are referring to. And these are in fact copies of the references. And then the other type of reference you can have is a mutable reference, which does allow you to modify the value that we have borrowed. But then we have to be careful, because we have to make sure that we don't have two threads, for example, trying to change the referent at the same time. So there are rules around this. And if you have a mutable reference to a value, then you cannot have any other reference to that value active at the same time. So this will hopefully feel familiar to you, in the sense that there is a principle called the multiple reader or single writer principle, which is a principle designed to handle issues of concurrency and to stop threads interfering with each other, for example, and to stop corruption. So I'm hoping this makes sense, that if you get this reference, it's a mutable reference so that you can write and change the value you're referring to, then you can only have one of these at any one time, and you can't have other references active at the same time, because if you did, then there would be a problem that, well, either if you had another mutable reference, then maybe you would have updates to the value that would get out of sync or would be ignored or overwritten. Or maybe if you have shared references, then they would maybe be holding stale values. So it's to try to keep the link between the reference and the value correct and up to date, and make sure that you don't override something and that you don't get a stale value. So those are the rules you need, that you have around references. And I'll come on to some examples of the lifetime rules as well in a second. I've got an example of some code with that. And then just to say, you can also do dereferencing, as you can see here. So we've on the second line here, we've borrowed the value A by creating a reference to it in B, but then we can dereference that on the third line, as you can see there, to go back to the to show the original value in A if you need to do that. And you can, in fact, do this at multiple levels. You can create references of references. You can dereference multiple times as well if you want to. But yeah, I don't think we need to worry about that. Now, this, as I said, there's the rules on the lifetimes of references as well. And I've got an example here, and this is quite difficult to get to grips with, I think. So I would suggest you sort of take it away and have a think about it. But what it is trying to do is to make sure that the reference and the referent are always kept in sync, that their lifetimes are not going to be problematic. So here we have the value A that's going to get borrowed and become, we get the reference X here. And any reference to that must not outlive the value itself, because then that reference will be pointing to something that no longer exists. So this gives us a constraint on how large a reference's lifetime can be, because of the lifetime of the things it is referring to. So in this case, if it's outside these dots, then it's going to be problematic, because that's the scope of A effectively here. So the last line here is going to be, when you try to dereference the X here, that's going to be problematic, because A has now gone out of scope. And then you can look at this from the other side, and if you're storing the reference in X, then that has to be good for the referent has to be good for the lifetime of X as well. So this says this gives us got a lower bound on the value of a reference. So if you put those together, what you end up with, which does work, is this kind of situation where the value that we're going to borrow, A, here, is in scope for the whole of this piece of code. We borrow it within this block in the middle here, and we can dereference it, and everything's fine, because that A value is still in scope. So yeah, that all works fine. So that little bit is perhaps a little bit more complex, but if you sort of try to break it down to think of the two sides, and making sure that the reference and the referent are still in scope and still valid, then you can sort of work your way through that and understand the problem that it has there. There is more detail to this, and you can specify you can put in specifications about lifetimes, which I've not gone into here. There's a tick operator to do that, but I think that's getting more complex than we need to do at the moment. But if we need to, we can come back to that. But I'll say is the best idea really is try to keep things simple, and use to help you with the ownership problems is, use shared references when you want to borrow a value and then pass it around to be read, maybe passing it to the functions to be printed or something like that, whatever it is you're trying to do with it. But always keeping in mind that we have to have the owner, and we have to make sure that that owner is still referring, still owns a valid value, and that value also has a valid owner. Okay, so yeah, have a think about that. Try it out. There is a bit of a steep learning curve on that one, but it's, if you practice it and try out some examples, then I think you'll get the hang of it. Now we'll move away from that topic now and go on to something I don't think I mentioned it when we were talking about arrays, so I just wanted to go through it. This is the idea of a slice, which is one way I like to think of it is it's almost like a window that kind of can move along an array. It's a way of taking a subset of an array or some part of an array, but doing this quite dynamically, because you can specify how big this window, this slice, is going to be. And yeah, a great way to do it, because of the ownership idea, is that you can borrow a section of an array. So you don't want to take ownership of part of the array to do this, or ownership of the whole array, but you can borrow a section of the array to do that. So this piece of code here, we've got a function at the top that we'll come onto in a moment that is borrowing part of an array. But if I go through the code, we've got some x's here. So these are integers. We've got 5 of them in our array. Then we've got another array here of some y's, and these are all being initialized here. And then we can specify, we can print out some values of these with using the indexing. So just showing the 0 index there. We can look at the length, and we can use this. The memory package gives us a function to look at the size of things, and here we pass in a reference to our x's here, so our array, and then we want to do this analyze function, so we can borrow the whole array for that. So this will then pass that into here. We've called it a slice, but in this case, it's a slice that has the size of the whole array, so we can pass all of that in, and then you can be more specific. You can shorten the size of the slice if you want, so you can borrow just a section of the whole array. So in this second call to the analyze slice here, where we're looking at our y's array, we're just taking the elements 1, 2, 4, and so we pass that into the function. So we borrow those and pass that into the function. And if you try this, the next one with this out of bounds, because of this is the wrong length for our x's, so that will cause an error, and our compiler can pick that up because we know the size there. Okay, so that's an example showing slices, but also shows some examples of borrowing as well. Okay, there's more examples. There's some links there to go into it in more details if you want to follow those. But this is slices are quite useful, and often if you're using arrays, this is quite a useful way to handle sections of an array, or to go through parts of an array and pull out some chunks of that and deal with those without having to deal with the full array. Okay. Now on to some more general points. And error handling. This in Rust is similar to ideas in other languages, so I think you will find these familiar, where we have the notion of errors that are recoverable and errors that are not recoverable from. And excuse me, these are handled differently. Recoverable errors, these are more day-to-day, and these are the types of errors that we would expect to happen. And I've already mentioned this enum result, which gives us back a choice of values, and a good way to handle this, handle the possibilities there is using matching. So, for example, if you have a file you're trying to open, it's not too surprising that maybe the file will not exist, or you'll not be able to open it for some reason when you try to do the open operation. So it's to be expected that you would have to handle an error from trying to do an open. And so for that reason, the open method here returns you a result. So either it's going to return you a file, so that's the OK value, so that's the happy path, that's what we want. Or if for some reason it can't open that file, then we would have an error returned to us, and then we can, with matching, as you can see here, we can then specify some statements to do some type of error handling, whatever it is you want, however it is you want to deal with that. And it may be that you want to propagate that error back up the stack. You may not want to deal with it there, which is perfectly fine. So you can do something like this, for example, return and just throw the error back up the stack to be handled by whatever called this particular function. But yeah, just to emphasize that this is a type of error that you would be expecting. So this is a recoverable error. You know that this could happen, and so you have a way of dealing with this, a way of dealing with the fact that a file cannot be opened. Just to say, there is an operator that helps you with propagating because this situation is fairly common. So you can use this the question mark on the end of the operation here, this expression, when you do the open. So this sort of takes the place, is sort of shorthand, I guess, or shortcut for what we were doing earlier with the matching. So either you get the OK and the file, or otherwise you get the error would get propagated back. So it's just saves you having to write the matching code for yourself, because this is a sort of standard way of a standard pattern that you would have. So that type of error are recoverable errors. Your code should be able to proceed even though you haven't been able to find a file. I mean, it may be that you'll return some message back to the user to say that that file is missing, but you can deal with this. It is an understandable situation. Yeah. The other thing, though, is that we could have unrecoverable errors, and so these are more unusual, and these are not things that we are expecting, and they really indicate that there is something very problematic happening. There's some kind of bug in the code, and that the fact this has happened means the code is not working in the way that you think it is working. So there is no really safe way that you can continue, because your code has got into a situation that is unknown. And if we get into that situation, you can use the panic macro, and this really this tells runtime to really unwind and clean up as much as possible and quit as soon as it can, because there's really no way to safely continue. And you can put in an error message as well if you have a panic. So if you're using this with some kind of an assert or something or whatever, then you can put in an error message. But this is really a kind of situation where you're not expecting to be in this situation, and there's no reasonable way that you can carry on in your code. The state of your program is not one that you want to continue with. Okay, and as I say, there's a link there to the docs about where the different sort of semantics where that you would use each of those. Okay, so yeah, we're getting just checking the questions in Slido. So yeah, again, those answered. Okay. So I'll move on now. So that was error handling. I'll move on to something called traits, which are similar to interfaces in other languages, and they're a way that we can define the behavior that a certain type has, and a way of sharing that behavior with other types. And when I say behavior, I'm really talking about the methods that we can call on a particular type. And it gives us the ability to group together data types according to functionality. And the way that they're defined is as this. So we say trait, and then we give it a name. So in this case, the name is summary, and then we define some behaviors that this trait has. So I'm saying here that there's some function called summarize, which has a particular signature, and that is what is the trait. So you can see this is similar to what we do with interfaces in other languages, where we define function signatures but no body. And then if we're going to use this trait on a particular data structure, for example, here we have a struct, and we're going to we want this struct to follow this particular trait. So we use the impl keyword here, specifying the trait we want and what it is applied to, and then we can specify how that particular behavior applies in this particular case. So for this particular struct, how this would be handled. So some specific behavior that you would have. So as you can see here, it's doing format. So it's creating a string in a certain way, putting together two sets of information here, and these are made up using the struct that we have here. So we're using the username and the content. And so when we say summarize, what it's going to do is create this string, which is concatenating the username and the content in a certain format. And because this is the last line of this function, then that is the return value. So that's why we are returning a string here. So it's a way that we have of saying that certain data types will have some behavior, and then we can specify what this behavior is specifically for those particular data types. Okay. It may be that you want to have some default implementation for the trait, so you can do that by applying some function body here. So as you can see, if there's no, if a data type then doesn't give an implementation, then it will use this default one. Okay. Then how this can then be used is the kind of the similar to polymorphism in other languages, is that you can then, when you have some function that is expecting a particular data type as an argument, then you can use this, you can specify this trait. So what you're saying effectively is, I want some data type as an argument here, and I want one that implements this particular trait. So if it implements this particular trait, then this function then it will be able to be handled by this function. So as you can see here, we pass in the data type that implements our summary trait, and because it implements that trait, we know that we will have this function summarize available for us on that particular data type. So we can pass it in safely, and it will then apply the functionality as the behavior that is specific for the way that that trait has been implemented on that particular data type. And so this particular piece of code here could be used, and we could pass in many different data types that implement this trait in different ways, and it would always choose the appropriate implementation of that depending upon the data type. Okay. This is a lot to chew. Okay, so all right. So well, you'll have practice of this hopefully, and we can go through. So do try these things out, and we can cover it again in a later lesson. And if you have questions, please keep putting them onto Slido or into Discord, and we can try and answer them. I think once you've tried these things out a few times and tried some examples, you will get used to these ideas, and it will become sort of second nature to you. But yeah, certainly, if you do have questions, we'll obviously do please ask them. Okay. So what I'm doing actually in this lesson is I'd started off with very specific language functions, I guess, or features, sorry, and I'm sort of moving away from that a little bit now and getting to do things more generally. So things hopefully are getting a little bit easier, a little less complex, a little less abstract. Okay. So in fact, we finished really with the very language-specific items, and we're going to talk now about a tool, Cargo, that you may well have come across, and it's a tool that we can use to compile and build projects and manage dependencies. It's a very useful tool. It really does everything for us in Rust. You can use Rust-C, the Rust compiler, but that is just the compiler. It doesn't do the other things that Cargo does. So when you're creating projects and building projects, you will tend to use Cargo rather than anything else. And you can use it as in this example, to create a new project. So you can say Cargo new, and you pass in an option. So the one I got here is bin, and then a project name, and it will create a package for you in the directory for that name. And the bin option here means that it will give you an executable file as a result, rather than it creating a library. And it gives you a certain structure if you do this. So under the Bootcamp directory, it will create a source directory with a main file, and it also has this the Cargo tobble file, which has details, metadata for you. As a default, it will create some code for you, so it creates your little hello world within a main function, just to show you how to get started. And then the metadata that you get in the file, it's details about the package. So obviously you can go in and change these around. And then it has a section where it will allow you to specify dependencies. So if you're creating an executable that is dependent upon other packages, then you can specify those packages so that when Cargo is building the file, it will know to go and get know how to get the dependencies. And once you have this set up, if you want to build and run the project, you can just do cargo run, and that will build the executable and run it for you. I just printed out some of the other commands that you can use. I think these are all straightforward. It's similar to npm, I guess. So the node package manager, if you've used that. Yeah. So the ones you like to use, I guess, are things like clean, run, and test. Yeah. And then the way that we bundle together our code in a sort of meaningful way is, as I mentioned, a package and creating a package, and then we have the idea of crates and modules. So a crate is part of a package, and the cargo metadata file will describe how to build those. And the crate is meant to be grouping together some functionality in a way that would make sense to be shared with other projects. So you can expose some functionality to other projects. There are some restrictions. So a particular package can only have one library crate, but can have many binary crates within it. And you can further refine these things by setting the privacy of the code, so showing what's public or private within that, what's visible to other projects. And you can do this with the pub keyword. Yeah, the hierarchy is like that. So you have a package and then crates and then modules. Okay, so that's all of the theory. I'm sorry, it's a lot to take in. Just let's have a look at the questions. So to use Panic, yeah, I've put a link into some documentation about that. What was it? So Panic is really in the case where there's no way to recover from some situation, and it's not this sort of everyday error that you would try to handle and you could handle safely. It means that there is something seriously wrong in your code. Your code is in a state that just doesn't make sense, and you have to stop execution as quickly as possible at that point. Okay. Okay, I think we've got answers for all of the rest of the questions. So okay, so yeah, we'll finish there then. Please carry on with the homeworks. So I think some of the homeworks will make more sense now as well, that we've covered all of the other bits to do with references. So please do carry on with those. This is going to be the last lesson for the time being. We're going into sort of dealing specifically with Rust. We have enough now to then go on to use it, and we're going from tomorrow. We're going to start. We'll move on to looking at Solana in more details and get coding on in that. So I'll finish there. As ever, please ask questions if you have them. We'll stay around for the next half hour to answer questions. And yeah, please carry on with the homeworks as well. Otherwise, I'll look forward to speaking to you tomorrow. Thanks, everyone. So the question about is panic similar to error in, or sorry, the reverting solidity? Yeah, that's a good analogy, I think. So in solidity, you have the idea of things like require or error, where you're looking for something specific, and those are the kind of recoverable errors that you can handle, and the corresponding keyword to in solidity to panic is the assert. So in solidity, you have the assert, which means you've got into a kind of an unrecoverable state, whereas yeah, which is the sort of semantic similarity to panic in Rust. Yeah. Yeah, it looks like I've got a typo in the notes, so I'll fix that and send those out again. Yeah, to do with a push. Yeah, I'll fix that. So there was a question about proof of history in the technical questions channel, which I can clarify that when they're talking about the fact that an application can hash data, what they really mean is that they're trying to warn against using the values of the hashes as something random, just because the fact that people can put data in there and therefore manipulate what is in the hashes to some extent. So it's really they're just talking about the possibility of saying that it's not entirely random, because there is some possibility of changing the values. So it's really just a point of sort of security point, I guess, to say you should be careful about that. The fact that there is some degree of control there, because people can get involved and change the hash value by putting in data. So that's what that is about. The question about, is it possible to bypass ownership rules? There is the unsafe keyword that you can use to relax some of the restrictions, but I don't think it completely bypasses things. I think there is still checking going on there. But really, you wouldn't, well, it should be rare that you would want to do that, because the rules are there really to make sure that your code is safe and that you're not going to get problems at runtime. So yeah, it's not something you should be wanting to do. Yeah, we're not starting on Encode tomorrow. It's going to be more Solana specifics. It's going to be Web3 and more details around Solana, but not Encode just yet.
Great, thanks everyone. Thank you, Lawrence, for the session. We'll pick it back up tomorrow, same time, same place. Looking forward to it, and see you guys then. Let me know if you have any questions or any concerns or feedback. I know some people are asking about kind of team groups. Let me know if you want to try to spice up teams and to kind of meet more people. We can look into that as well. But that's it. Have a good one, and see you tomorrow.